Hey guys, welcome to Chapter 1 of AP Calc. We're going to start off on Section 1.2, which is finding limits graphically and numerically. So just a little heads up on the notes. You can see anytime that there's like a box around something, so you can see this box here. That's a definition or a theorem that I want you to look at. So we're going to start off by looking at this notation right here. It says find the limit and then let x go to a of the function f of x equal to L. So what this is saying is, we're going to sketch a couple graphs here. Okay, and what we're going to do is we are going to let x approach a, so let's put an a on both of these, and then we're going to draw the same graph. They're going to be the same graphs except at a. So right here at a, we're going to put an open circle, and this is connecting. And then over here at a, we're going to actually have a point that exists. So we're going to call this capital L and this capital L. So what this is saying is as x gets close to a on the function f, let's label this f of x. Okay, so as x is getting closer to a, the function gets closer to L. And I wrote this for you 3 times up here. You can see these 3 cases here. Different ways to word them. You can go through and read that. So notice it doesn't say x has to equal a. So if you can imagine flying in from the left and then flying in from the right. So if you had like 2 flight paths, where they would meet up, or they should meet up, I should say, is going to be the limit. Over here, if you fly in from the left and if you fly in from the right, where they should meet up is the limit. So both of these cases represent the situation where x is approaching a of the function equal to L. Underneath this, remember, limits are not concerned with what's going on at x equals a, so who cares if a exists in the first case or if a doesn't exist in the second case. Limits only care about what's going around it, not about existence. So that's a big thing we're going to keep talking about today. Okay, on to example 1. So example 1, I asked you to graph this, but I also asked you a whole bunch of other things. First of all, looking at this, do you have any idea what this function is? Okay, then we'll figure that out as we go through it. How should we restrict the domain? So first, look at the bottom, the denominator. The denominator cannot be 0. So what value of x would make the denominator 0? And you can see if x is 2, we have a problem here. So we're going to say x can't be 2. Why? Because the denominator can't be 0. Okay, how does this affect the graph? Well, we'll find out what's going on with that in a second. Now it's saying using our graphing calculator to graph the function. Before I start doing that, let me tell you that I know that it's not going to fit on here if we leave the scale 1 by 1. So let's count by 1s on the bottom, which we really didn't have to write that, but just to clarify. And then let's go up by 2s on the y-axis. Okay, so let's get out our graphing calculators. Okay, so on the graphing calculator, we're going to graph this. I'm going to show you a couple tips if you don't know them yet. Let's go ahead and hit y equals, clear out if you have something there. Now we have a fraction. We have a numerator and denominator, so a rational function. I don't like using parentheses with division. I'd rather use this feature right here. So you're going to hit alpha and y equals, and then choose number 1, or you can just hit enter, and you get a numerator and denominator. Okay, now that you have that, let's go ahead and type the function in. Again, that was alpha and then y equals. Okay, so our numerator is x cubed. So x cubed and then minus 8. So we have a difference of cubes there if you recognize that. And on the bottom, let's see if I can get down there. Okay, on the bottom is x minus 2. So we'll go ahead and type that in. Okay, go ahead and graph this. And look what shape we get. So this looks like a parabola. However, we know we have an issue. We just said in part, was it A, that we should not have a 0 in the denominator. So let's figure out, we're saying x can't be 2. One way to do this is if you want to pull up a data value on here, if you hit trace, and then just type the number 2. So I want to know what's going on at 2, and then hit enter. Do you see how it didn't give me a y value here? So because the graph doesn't exist there. However, if you go ahead and hit trace and let's type in the number 1, we can see that we get a 7 out. If you were to plug a 1 into that function, you'd get a 7 out. So one thing I'm doing, the one reason I'm doing this with you is to show you, even though the graph looks like the function exists everywhere, we have to know enough to know that it doesn't at 2. So the graph could be misleading. We just want to be a little careful with that. Another thing, if we want to go and graph this now quickly, if we hit table, we can go ahead and plot these points. So I'm going to go ahead and do that. You go ahead and do that as well. Okay, so as you can see, I started plotting some points. Go ahead. I'm just getting these values from the table. You could quickly plug substitute numbers in also. At 1, I got 7, 2, 4, 6. Remember, you're counting by 2s. Now, I know at 2, the function isn't going to exist. There's nothing that I can put there. So I'm going to go on to 3. Again, I'm just looking at my table. And 3 is 19, which is way out there. So I really don't know how to continue this. I can see that this is going to look like this, but I didn't know what was going on at 2. Maybe if I go ahead and sub in 1, 2, 3, let's look at -4. Okay, so if you sub a -4 in or use your table, you're going to get 12. 1, 2, 3, 4, 2, 4, 6, 8, 10, 12. Okay, so you can see the symmetry. You can see that there's going to be a hole here. Remember, our graph didn't show us our hole. A graph showed that the function kept continuing, but we were smart enough to know that x couldn't be 2 because you can't have a 2 in the denominator. So how does this affect the graph? There is a hole at x equals 2. Okay, going on using a graphing calculator. We already took out C. Okay, now we're on to D. When we have a function, if it doesn't exist at a value, what we're going to say is at 2, we know the function doesn't exist. We're going to write a D and E right there. Okay, now to get the rest of the values, you can see that we're starting about a quarter away from 2, and then we're creeping up. We're a tenth, 100th, and 1,000th. So the gap keeps decreasing. So you really can't use your table mode like you're used to, where because it's counting by the same amount, like the same increments. So a quick way to do that is to go to your graphing calculator. Okay, and on the graphing calculator, remember I told you before that if you want a value, so let's start on the left at 1.75, go ahead and hit trace, type in the number 1.75 on the bottom, go ahead and hit enter, and you see that you get 169/16. Okay, I went ahead and changed that to be decimals. So now we're going to get 10.5625, so we could record that on our table under 1.75, and we're going to type another one in, and we're now going to go 1.9, so we're getting closer and closer to 2. Go ahead and hit enter, and you get 11.41. So I'm going to go ahead and fill the table in. You guys practice this by hitting trace and your numbers, and we'll meet up at the notes. Okay, I went ahead and filled this in. Let's go from the left. If we start over here, you can see that the data starts at about 10.5 if you're at 1.75. Let's get a different color here. Okay. So we start here at 10.5. Do you see as we move over 11.4, 11.94, 11.994, you're getting closer and closer to what number? Okay, now look on the right side. We started about 13.5, and as you creep in from the right, 12.6, 12.06, 12.006, do you guys see that the numbers look like they're meeting up at 12? And if you look over here, that's where that hole was. It was at 212. So looking at the graph now, do the points 1.999 and 2.001 exist? Sure, what's the only value that didn't exist? Wasn't it 2? So even though the Okay, so on to F. What does it mean to get closer to something? It means the X value approaches the given number. Okay, and I talked you through E, but we didn't actually answer it by writing it. It says from looking at your graph, do those points 1.9999 and 2.001 exist? Sure they do. Remember, like we said, the only value that didn't exist was x equals 2. And then it says, as we get closer to 2, does the graph exist? Sure does. Just not when x is 2. Okay, going on, it also says on G, another way of saying that a function gets closer. So what was our function getting closer to? Remember, it was getting closer to 12 from both sides as x got closer to 2. That here is what we're allowed to say right here, that the limit as x approaches 2. So as x got closer to 2, here's 2. So as x came in from the left and as x comes in from the right, we get closer to 12. Who cares if x exists when x equals 2? We only care what's going on around it. Okay, so the biggest thing about limits is they're going to give us a way to talk about a function when the function doesn't exist at a certain value. Okay, so one way we're going to learn is looking at this picture of this bridge here. Before we go on though, this note on top, graphing and tables aren't always the best method. That table, that was pretty annoying to write all those numbers out. Hopefully in the next couple days we'll learn a better way. And then graphing, we saw that that could be misleading. It looked like x existed at 2. So, and if you don't have a graphing calculator, that could be a little tricky. So in a couple days we'll look at how to analyze limits analytically. Okay, before that though, we're going to refer to this picture a couple times in this chapter. Let's say you wanted to cross this bridge. Okay, what 3 things would you need? Well, first of all, what's missing? You can see there's a bridge. So let's say you're coming in and you're driving along on the left. Okay, so you're over here driving along on the left. You're going to need 3 things. Okay, so the first thing you're going to need is you need this road on the left. Okay, what else do you need? Well, you're driving along, all of a sudden the road ends right here. So what do you need that to be? You need that to be your bridge. And then as you keep going, you need the road on the right. If you remember on that picture I showed you on the last page, how as x approached 2, the value approached 12, that's kind of what I want you to think about here. So as you're approaching the bridge from the left and the right, do you see that the roads meet up? Right? We just are missing this bridge. So we're going to use this example to illustrate what we mean throughout this chapter. Okay, so we need the road on the left, we need the bridge, and we need the road on the right. So based on that, in this picture, can you cross? Of course we can't. What's missing? The bridge. Okay, if you were to build a bridge, would you know exactly where to build the bridge so that we could then cross? Sure, wherever this gap is. Where the left meets the right, that's where we would build the bridge. We sure would. Okay, so as you can see, whether the bridge exists or not does not matter about the roads coming in. Okay, so this is why a limit's important. It gives us a way to talk about the activity going on in the neighborhood of a point, whether the point exists or not. Again, remember on that last graph we saw 212 didn't exist, but we could still talk about what was going on around it. Okay, and like I said, we'll use this later in the chapter. Okay, now we're going to look at left and right hand limits. I've mentioned them as we've been talking through this, but now we have some notation. So if you look right here, it says if we want the limit as you approach from the left hand side. I love highlighters. If you guys want to use them on your notes, that's awesome. Instead of writing left hand side every time, do you guys see this little superscript here? That means the left hand side. And if you want to approach from the right hand side, do you see the superscript of the plus sign? Just like think about a number line. If this is 0, you have negative on the left, positive on the right, same idea. Okay, so this next sentence is key. In order for a limit to exist, the left limit has to equal the right limit, then we can say the limit exists. So if you look right here, can you see the superscript, the left limit, the right limit? If they're the same, then we can say the overall limit exists. So basically what this is saying is if you have this value c here, I'm just making up this function real quick. If you come in from the from the left and the right, they have to meet up. And do you see how this analogy relates, or the bridge analogy relates to this? As you come in from the left on the road and the right on the road, who cares if the bridge exists? Okay, you could also have this case where the bridge does exist, and again, it doesn't matter. Okay, the limit's going to be the same. We just need the 2 roads to meet up. Whether the bridge is there or not, who cares? Okie doke, going on to the next part. Okay, I gave you 2 piecewise. We're going to be dealing with a lot of piecewise this chapter, and I just want you to get familiar with them. I know you don't see them quite often. I want you to notice the difference between the 2 piecewise. This on the right, you have a function here, so x less than or equal to 4 and x greater than 4. So 2 separate pieces, one to the left of 4, one to the right. Whereas this one, this is saying when x is 4, the output is 1. So this is like an ordered pair. It's an input and an output. So it's saying at 4, we're going to get 1. Let's use a different color here. So at 4, 2, 3, 4, we get the 0.1. Then it's saying everywhere else. So anytime x isn't 4, we're going to get 3, which is just a horizontal line. So everywhere else, we're going to get 3, 1, 2, 3. Try to make this as straight as I can. But remember the condition, x can't be 4. Okay, so now let's go through and it says find the limit as x approaches 4. So look, here's 4. Okay, so as you approach 4 from the left, do you see coming from this way? Who cares about this point right here? We're looking at the function and we're saying as we're driving on our road from the left, we end up here. As we drive in our road from the right, we end up here. So the limit, we could say the limit as x approaches 4. Don't forget to write this. A lot of times you guys leave this piece off. You want to say the limit of what you're dealing with. So the limit as x approaches 4 is 3. And the reason that this worked was because the left and the right limits matched up. Okay, going on to the next one. If we go ahead and graph this, we're saying anytime x is less than or equal to 4, we're going to use this top function. So again, let's go over to 4. 1, 2, 3, 4. Okay, so I'm going to sub a 4 in here and you're going to get a 5 out. I'm going to zoom in a little here. Okay, 1, 2, 3, 4, 5. Okay, when x is less than or equal to 4, so I went ahead and subbed a 4 and got a 5 out. Do you see a slope of 2? So you can either graph with slope or you can graph by plotting points. Y-intercept is also -3. Really, whatever's quickest for you. Then you can just see a slope of up 2 over 1. This should match up. Yep. Okay, so we get this line on the left. Now, okay, now as we go to graph the second one right here, it says that x is greater than 4, but we can go ahead and sub a 4 and just make it an open circle. So if you go to sub a 4 in here, you're going to get 5, and you can see that they meet up. Slope of -1, down 1 over 1, down 1 over 1. We're just trying to get an idea here. Okay, so you can see by looking at this that well, let me write down what the problem says. The limit as x approaches 4 of the function, this is what they asked. They said find the limit of f of x as x approaches 4. Here's 4. Fly in from the left, fly in from the right, or drive, either way, and you can see that they both meet up at 5. Okay, again, the limit exists because the left and right-hand limit were the same. Just to point out, if you guys were, I'm just going to draw a little picture up here. Let's say your piecewise look like this. So this was one line, and let's say the second piece of the piecewise didn't match up here. It went here. And if this was the value 4, do you see that the limit from the left and the limit from the right don't meet up? So the limit in this case wouldn't exist. But the one that I showed you have the left and the right meeting up, and that's why the limit exists. Okay, oh, that got really big. Okay, so one thing I want you to notice, when you have a piecewise like this with 2 different components, so 2 different pieces, what you're looking for is the left to meet up with the right. When you have this one with the function is the same except at a point, who cares about this point? It didn't really affect it. You didn't have 2 separate pieces to the left and the right. Okay, so note the difference between existing and approaching. We didn't really care. Here the function didn't exist here. Here it did. It really didn't matter. We're looking for left and right meet up. You have 3 cases here where limits don't exist. One is unbounded behavior. So if we were to sketch this quickly, you can see that at -1, you have an issue here. So at -1, let's get a different color. We're actually going to have a vertical asymptote, and we'll talk more later in the chapter about how to know if you have a vertical asymptote or a hole. Some quick points we can look at, like 0, 1. And I'm just going to do a quick sketch. We're just trying to get a feel for this. Okay, now look what happens. As you approach -1, which is what they're asking for, here's -1. Now note -1 doesn't exist and we don't care. We're just approaching it. As you approach -1 from the left, do you see the left goes up to positive infinity? Approach -1 from the right also goes up to positive infinity. So because the left and the right both went we could say the limit as x approaches -1 of f of x equals infinity. The left and the right were both infinity, so we're good to go with this answer. Now infinity, right, we're never really going to reach it, and that's why it's in this limit not existing section. Okay, the next one. Now this function, again, we'll see a couple times. I'm going to rewrite it as a piecewise and see if it helps you. At 0, if you guys try direct sub, okay, so direct substitution is what you would always want to do. You can see here we had an issue with a 0 on the bottom. Here we're going to have a 0 on the bottom. And here, well, let's just stick here. Okay, so as you try a 0 on the bottom, we have an issue. So now we're going to try graphing it to see if it makes sense and to see why is this not going to exist. Let's try subbing in positive numbers. Think of all the positive numbers, pick one. Let's look at 5. What if you take the absolute value of 5 over 5? Do you get that the absolute value marks are irrelevant here? So we're always going to get the number 1. So anytime x is greater than 0, you're going to get 1 because the absolute values are irrelevant. Now, what if x is negative? Again, think of all the negative numbers. Let's just pick an easy one. Let's look at -4. For no reason, I'm just trying to get you to think through this. If you take the absolute value of -4, you're going to get 4. But what's just the value of -4? Now you're going to get -1. So if you sub a negative value into this, because they're both x's, but one's positive and one's negative, you'll always get -1. Remember, we're not subbing 0 in because the function doesn't exist when x is 0. So anytime x is greater than 0, you're going to get a constant 1. Anytime x is less than 0, you're going to get a constant -1. Do you see now why this limit is on here non-existing? Because the left road does not meet up with the right road. This right road goes to 1 and the left road goes to -1. So that's why that won't work, because the left and the right are different. This last case is going to be pretty obvious. It's called the oscillating behavior that you're looking at. And on this one, see this craziness over here at 0? What happens is you can't really narrow down the left and the right because it's going so crazy. They say right here that the function does not settle down. Okay, so this is going to be a case where you can't find the limit. Moving on, remember the limit is only concerned with what's going around x equals c, not when x equals c. Okay, let's sketch this graph. So now we're going to do some examples. If you want to pause it and try some of these on your own, that would be great. And then you can just catch up with me and see if you got them right. If we're asked to sketch this graph, if we're looking at function notation, I want you to see here that f of -2 is 0 is just the same as saying -2, 0. That's an ordered pair. Same thing here. Then we get to some limit stuff. So how about we take it easy and let's start by graphing these ordered pairs. So at -2, 0, we have a point, and at 2, 0, we have a point. Now they say the limit, this third piece, as x approaches -2 is 0. Here's -2. As we approach from the left and the right, we have to meet up at 0. So I'm just going to do this from the left and from the right. It really doesn't matter. I just want to show coming in from the left, we are here, and coming in from the right, we are here. Next case, they say the limit as x equals 2 doesn't exist. See if you can remember from the previous page the 3 cases when the limit doesn't exist. The first was unbounded behavior, where your answer for the limit was positive or negative infinity. It was also the left and right not meeting up and oscillations. I'm going to go with the second case of the left and right not meeting up. So at x equals 2, the left and right can't meet up. So I'm just going to continue this on, but I cannot continue past this, because if I draw a line here, or some piece of a function, the left and the right would meet up. So I'm just going to go up here. Now I have a case where at x equals -2, as x approaches 2, the left and the right don't meet up. And then we satisfied all those conditions. And we're good. Okay, next couple examples to wrap this up. It says example 5, and then within them there's other examples. We're just going to go through and answer these questions. Notice that they're asking 1 from the left. See the superscript up there? Here's 1. Drive in from the left side. Where do you end up? At 1. Do we care that there's an open circle there? Not at all. Limits don't care about existence, just approaching. 1 from the right. Drive in from the right. You end up at 2. Are the left and the right the same? They're not. So the limit as x approaches 1 cannot exist. This next part right here This is like an algebra 1. Do you see how they're just saying what's going on? So at x equals 1, what is the function? Look at 1. Where does the function exist? Right here at 2. Okay, since I circled this, let's go ahead and look at this one. At x equals 1, the output is 0. Okay, now let's go to the calculus. Fly in on 1 from the left, or drive. Coming in from the left, we end up, looks about negative 1.2. It's hard to tell. 1 from the right, and you end up at 1. Is negative 1.21? No way. So the limit doesn't exist. Also, you can see the left and the right don't meet up. You cannot build a bridge to connect them. Okay, going on. Oh, look at these. So these functions are almost the same. We just have a point here. Okay, so as we approach 1 from the left, here's 1. Drive in from the left, and you're at 1. Here's 1. Drive in from the right, and you're at 1. Do the left and the right match up? Are they the same number? For sure. Also, you can look here, and you see at 1, if you drive in from the left and drive in from the right, they meet up right there. That's why the limit is 1 also, just by looking at it. At 1, what's the output? Well, at 1, there is no output. Although I'm going to refer to these problems as like algebra 1, where you're just doing function notation. Over here, at 1, what's the output? Negative 2. Jump to the easy one first. Now, 1 from the left. Here's 1. Fly in from the left. Where do we end up? At 1. Fly in from the right. Where do we end up? At 1. Is 1 1? Sure is. Limit is 1. Okay, going on to the next one. Zero from the left. Oh, you know what? Look at this one. So the difference here is that, do you guys see that there's no holes or gaps or asymptotes? So this one's different in a good way. 0 from the left. Here's 0. Come in from the left. You're at 1. 0 from the right. Come in from the right. You're at 1. Is 1? 1? Sure is. Left and right limits as we approach 0 are the same. At 0, we get an output of 1. That was a whole bunch of 1s. Next one. As we approach 2 from the left, ooh, look at 2. You guys see this asymptote here? Okay, so as we approach 2 from the left, because the superscript is negative, it flying in and we shoot up to positive infinity. 2 from the right, here's 2. We go down to negative infinity. Is positive infinity the same as negative infinity? No way. So the limit does not exist. Output at 2, vertical asymptote, there is no output. Okay, last 2. Okay, guys, we're almost done with our first lesson. Look at these 2 graphs. They're almost the same again, except example 8 has a point at negative 2, whereas example 7 doesn't. So since we're talking about that, let's go right here. At negative 2, algebra 1, the output is 0. At negative 2, there is no output. You have a vertical asymptote. As you approach 2 from the negative 2 from the left, here's negative 2. Come in from the left, up to positive infinity. Negative 2 from the right, up to positive infinity. If left is the same as right, then you're going to get infinity. Now, if you go back up a couple pages and look at 3 cases where the limit doesn't exist, one of them was unbounded behavior. So even though we got an infinity here, sometimes your book might call this DNE, for does not exist. We're going to ask that you write infinity so that we know why you know it doesn't exist. Okay, so this is an acceptable answer. Your book might give this, which is also acceptable. Negative 2 from the left, almost exact same graph. Positive infinity, positive infinity. If left and right are the same, we get infinity. And that's a wrap, guys. I hope this was okay. Next time I see you, please ask any questions on these notes that don't make sense or you need clarification on. Okay, see you later.